I feel this topic has been addressed. This problem has been mentioned a couple of times already, so I just wanted to lay it out there and formalize this problem that has been bugging me for a while, and I don't really know exactly how to think about it and make progress really on that. So the basic question is really, we have these two classes of operations that have been mentioned over and over again during this conference. Thermal operations, right, where you take your system, you make it interact with a heat bath with an energy conserving unitary, trace out the bath or trace out some subsystem. On the other hand, you have maps that have the property that they fix the Gibbs state. We know that they're not the same not the same class of operations. Any thermal operation is a Gibbs preserving map, but Gibbs preserving maps don't necessarily have to be time covariant. There are Gibbs preserving maps that are not time covariant. So this class of operations seem to be bigger than this one. Now the question is, how bigger? What do we need to add to thermal operations in order to be able to implement any Gibbs preserving map? So the first things we know is, of course, any thermal operation is a Gibbs preserving map. This is what I just said. The other thing that we already know is classically, these sets of operations are the same. So really, there's something quantum here that we want to capture. So the way I'd like to think about it maybe is, right, so yeah, what is the other way to think about it is how resourceful are Gibbs preserving maps if I'm setting myself in a framework where I'm allowed to do thermal operations, right? That's another way of setting the question. So we know a couple things about, so if you parcel the results, or a few results going towards trying to make this connection. So first of all, if the Hamiltonian is trivial, these guys are noisy operations. These guys are unital maps. We know that they're not the same, but we also know that by investing a little bit of work, log delta, where delta is some accuracy, just by investing a little bit of work, we can recover, we can simulate, we can implement any unital map with a noisy operation. So if I give myself a noisy operation, but also a battery with some amount of work that does not depend on the system size of the other system, I'll be able to implement my unital map. So I would say that this case, I'm fairly happy with the status of this particular special case. The other special case is if I have a Gibbs preserving map that is time covariant, and I wish to implement it only on states that are that are also incoherent. So there we have some partial progress. I wouldn't say this question is solved. It's like we have an expression for the work cost you need in this type of thermal operation framework. But really, it seems like we need a bit of a new idea of how to address this, how to think about what we should add to thermal operations. And I think I was really encouraged during this workshop because I did see a lot of new ideas popping around through the various talks. So I'm really encouraged that we might be able to really make headway on this general question soon. One thing that we might want to, so the main thing we want to focus on is basically how do we add the coherence resources that we need to implement the Gibbs preserving map, while making sure that we can still account for work and that we're not embezzling a huge amount of work and allowing things that are much more than the maps we wanted to simulate. So first of all, maybe you should be thinking about including a battery in the form of how we heard Jonathan present earlier, something that has a lot of coherence, but that still allows you to account for work by looking at how this battery is shifted along the energy axis. And then there's another thing I appreciate was mentioned in the talk earlier by Thomas. I really appreciate that it was mentioned because it's something I think that has been bugging me also for a while. In thermal operations, we always assume at the end that this Gibbs state is in a tensor product form between the Hamiltonian is a non-interacting Hamiltonian between the output system and the thing that we're tracing out. So if that's not the case, well, you can imagine that a Gibbs preserving map doesn't actually technically require, if I only ask that the input Gibbs state gets mapped to the output Gibbs state, I could interpret that as being, well, I could imagine having some thermal operation that maps me to something that has an interacting Hamiltonian, and that just my map would have the property that this conserves the local reduced Gibbs state on that output. So there seems to be some leeway there to actually extend a bit this class of thermal operations, and I have no idea what we get in that case. What I do know is that if we do relax this assumption, this counterexample that we have that separates thermal operations from Gibbs preserving maps, you can implement it in that way. So that's one way for explaining that particular counterexample. So really, basically at this point, I think there are a few scattered ideas, but no clearer picture of how to, on my end, for how to make headway with this problem. So I really appreciate your input, and if you're looking for a fun but probably difficult project, happy to chat more. I also want to mention this problem is also formulated as problem number 46 on this site. It's called the Open Quantum Problems, and it's available at that web address. But if you just Google Open Quantum Problems and look up problem 46, it's going to be over there. Cool, thanks.
Thanks. Do you have any questions, comments, solutions?
Concerning the count example that disappears, like, why would you, for example, ask for thermal operations that you are allowed to have correlations between the Gibbs state, but not ask for Gibbs preserving operations? Like, in a sense, you could generalize both in the same way, right?
Right, but Gibbs preserving maps kind of already do that. All you ask is that there's some state that you fix, right? You're not saying anything about Hamiltonian interactions with the cells.
Okay, but I understood that you say, okay, if we don't essentially demand that our systems are non-inducting again, right? So that the Hamiltonian is the sum of the individual Hamiltonians.
In traditional thermal operations, that's what happens, right? I'm saying that if you extend that, maybe you get to a class of operations that could actually cover all of Gibbs preserved maps. Right? I have no idea if that's the case. The point being that if you're allowed to trace out something that's interacting, that gives you access to something that looks like coherence in the eigenbases of the local reduced Gibbs state.
Okay.
Any other questions?
So this may not be the smartest question, but I'm curious on the relation between sort of these Gibbs preserving maps and information batteries. So obviously in some operations of these, everything that we interact with has zero free energy and we make sure it's conserved. But as you say, if we extend that, then we can couple with something with a certain amount of free energy, and then we simply account for it. That does give us a larger class of operations. So when we have these information batteries, is there any results about what we can achieve and whether we can reach Gibbs preserving maps if we have enough of them? Is that always true?
Right. So in any case, you need coherence, right? So with thermal operations, you need somehow to add this resource of coherence. But if you add a huge ladder of energy levels within the state that's very spread over the energy levels, and you give me enough work, blanking out, but I want to say you can implement anything. So.
But the work has to be returned, so it can be used kind of like a catalyst, but like we can't actually expend the energy at the end.
Exactly. The question is, how do we formalize that properly and show that we can actually implement these resources?
So that could be a way forward. Okay,
Yes,
thanks.
absolutely. Thanks.
Any other questions?
Yeah, sure.
Okay. I don't know, very nice lesson, but with maybe like, there's this concept of like approximate some operations. Like you relax this energy preserving condition, and maybe you can also relax the Gibbs preserving. So that you can, it's like this approximate operation or something. Do you think like that kind of approach might have some future?
That's a good idea. I haven't tried that. Two things that I might be worried about, maybe wrongly, is first, like, how would you motivate that physically? That you're allowed to do things that violate energy a little bit. But I guess you could motivate that, saying there's something else, some external, a little bit of source of coherence that you can exploit. No, I think that's a good idea. I'm not sure if that's going to give you enough coherence to do any Gibbs preserving map. But that's something I didn't check actually, so very good point, thanks.
Other questions?
Follow up to the previous, ignoring conservation of energy over short timescales is something that the particle physicists do all the time, right? So that's a well motivated by underlying physics.
I'm sorry, I'm not sure I caught that, I'm sorry, you're saying,
So particle physicists and their friends are perfectly happy to violate conservation of energy on short timescales, right? That's how particle creation
yeah,
happens.
yeah.
And so in terms of an approach that sort of is reasonably motivated, actually ignoring having conservation of energy be a long plan process and not short term process. Based on
Okay, that's interesting, I hadn't thought about it that way, yeah, thanks for pointing that.
I have one clarification question. So you mentioned that if the Gibbs preserving map and intersect the covariant maps acting on the covariant states. So the covariant states, you mean like the classical states, right? Or the quasi-classical states.
Yeah, those are the semi-classical states.
Right, so like, isn't it the same as the thermal operations, like you said, like the thermal operations equal like Gibbs preserving map?
I thought that it wasn't clear to me, but maybe I'm missing something obvious in the R.
Because output state should be also a classical state, right? Because it's.
Well, okay, so strictly speaking, they're not the same because you have the same issue of, noisy operations versus unital operations, right? You're gonna run against the same issue if your Hamiltonian is trivial. You already have a gap, but then we know how to get around that particular gap by adding just a little bit of work. I'm not sure it works. It's not clear to me immediately that it works also in this covariant setting. I would, we have like an expression for the word cost. Maybe it will just come out if you stared at the expression strongly enough, but I think I was a little intimidated and didn't manage to work that out.
Another question I had is like this noisy operation plus little work, like is that know that this is like optimal amount of work? Like for given operation, like can you get the optimal work that is like needed to implement this?
Depends on what you mean by optimal. It's clearly, okay, I can tell you this, the little work comes from a decoupling technique. So like information theoretic decoupling, you might know the paper that came out by some time ago, the thermodynamic meaning of negative entropy by Lydia Del Rio and collaborators and Renato and Vlatko and people like that. There they use decoupling techniques to show that you could, you could erase a system conditioned on a memory, and there you have some error terms in there, right? So the main entropy measure in this case is going to be equal to 0. So the mean term is going to give you exactly the 0 work cost, but you're going to have these extra error terms that are going to add up. So that's what I'm calling this little work. So it's near optimal, but it's probably not exactly optimal.
Okay, got it. Other questions? Okay, if not, let's thank Philip again. So is there any other open problems? Oh, I think there's one.
I don't have a USB. Can you put the slide that I see? I don't have a USB for in my laptop. I don't have a USB port.
You want to use a clicker?
Can you show the presentation, the slide from your laptop? I don't.
No, Zoom, like Google Zoom.
Right. Okay. Sorry. Okay. Hi. So the formulation of this problem is very simple. It's something that the formulation of this problem is very simple. It's something that I tried to do some years ago, and I only have a partial solution. So the idea is we consider the pure states of a bipartite system and the Hamiltonian of this. Sorry?
You meant that bigger?
Yeah.
Thanks. So you consider the pure states of a bipartite system, and you have the Hamiltonian of this bipartite system, and you know the spectrum of this Hamiltonian. So the question is, given a certain amount of entanglement between the two subsystems, what is the minimum energy that the states have to have, and which family of states attains this minimum energy? Okay, so that's the question. It's very simple, and it connects two resources: entanglement on the one hand and energy on the other. So what I found years ago was this partial solution in which I consider an Hamiltonian in which there is no interaction between the two subsystems. And yeah, the solution is this kind of states that when traced give thermal-like subsystem reduced density matrices. And there was also this nice thing that this solution could be extended to mixed states as long as the entanglement quantifier you use to quantify entanglement as the complexity property and reduces to entropy of entanglement. Okay, but apart from that, like I tried to solve this this problem. For example, you could consider the entanglement of each one of those states and like couple them in one with the other, like doing couples of that and seeing how the card entanglement energy, which kind of cards you can generate, but that didn't lead anywhere. So I mean, I have no practical progress on that, but yeah, if you are interested, you can try to solve this problem. Yes.
Just curious, if we set, if we think about those HA and HB as Hamiltonians for subharmonic oscillators, so this is just a question about a two-mode optics problem where that would be kind of like the minimal number of photons and minimal energy to reach a certain entanglement. That's solved? Is that solved?
So if you have no interaction,
Oh no, if HA and H, but yeah, if you have no interaction, you just have two optical modes, two simple harmonic oscillators, Hamiltonians just the number of photons, you know, and plus H omega. And then then you can of course ask what's the minimum number of photons to get the same amount of entanglement. I never thought about this problem, but I'm just curious, is that problem solved?
yeah, it would be a case of
So it would, so that would be right, so you, okay, I see.
and yeah, by the way, I have in the particular case, what comes out is a two-mode squeezed state.
Yeah, I have the feeling it was that, so that means that the part of it looks like a thermal state. I mean, if you take a partial trace, I wonder if that's a test for anything, general scale.
Sorry, can you repeat?
Because of course, if you take two-mode squeeze state, right, the local state looks like a thermal state.
Yes.
So I wonder if that is a property that generalizes.
I wonder that too in the interaction case. I can tell you in the non-interaction case, if you trace that, you get a thermal state, but it's not the state with respect to HA, but is the thermal state with respect to the eigenvalues A0 plus B0, A1 plus B1, A2 plus B2, etc.
Right.
But it's a thermal state.
That's an interesting problem. Try to think about it once.
So I just want to point out that indeed this is an interesting problem, and people in the group we come from in Vienna, so Markus Huber's group, have been more or less working on this problem for half a decade. So there is a series of papers with titles like Thermodynamic Cost of Creating Correlations, Optimal Thermodynamic Cost of Creating Correlations, stuff like this. The authors would be people like Markus Huber, Marty Perrenau-Lobé, Parnam Bakhshinizad, people like this. It's solved for d equal 5, up to d equal 5. More than that, it becomes very hard because it's a special case of the quantum marginal problem. So you want to create an amount of entanglement, right, such that the marginals look like thermal states, as you point out. So it's yeah, I mean, so they have even like majorization conditions and stuff like this for up to d equals 5. There's a nice polyhedron and stuff like this. But yeah, I just wanted to point out that there is like quite a large amount of literature on this, and that unfortunately they kind of stopped working on it around 2018. So whilst I think Marcus tries to trick every PhD student that joins our group to work on it, no one has tried working on it for quite some time because everyone is a bit scared. So I echo your sentiment that it's an important problem and that it's hard.
So we should just put it on undergraduate exam.
Yeah.
I know one of those two papers. I don't know if I know both. But is there interaction in that case? Because I remember they were starting from any thermal state, and with HA plus HB Hamiltonian and getting to other states through unitaries. But I don't remember there was interaction involved. But maybe it's in the other paper that I don't know.
I think Charles of time.
The choice of Hamiltonian was quite generic, and I mean, I would suppose you need interaction to get entanglement, right? So
Yes, I mean, in the physical way, like
Yeah.
you have to use a unitary and therefore turn on an interaction between the two subsystems, yes. But the question is not on the dynamics, right? But it doesn't matter.
Any other questions?
I was wondering, I'm not quite sure what would constitute a solution to this problem. Because, I mean, clearly it hugely depends on the entanglement structure of the eigenstate of the Hamiltonian. For example, if the ground state has the right entanglement entropy that you're looking for, then you can achieve energy zero. So what kind of formulation of a solution would you be happy with?
Yes, so something that looks like the one for the no interaction case. Also, I'm looking for solutions in the pure state. So for example, you say the ground state has maximal entanglement.
Well, I mean, for any entanglement entropy that you fix, I can write it down a Hamiltonian where the ground state has that entanglement entropy.
Yeah, okay. I assume that the Hamiltonian is given to you. You cannot change the Hamiltonian.
So you want it just as a map from Hamiltonian to states.
Yes.
Any other questions? Okay, if not, let's thank Nicole again. Oh, good. Other questions?
There's a twist on that. Instead of having the minimal energy, you have the minimal local free energy. And that would be an interesting question, I would think. How much free energy do you need to generate certain amount of energy?
Are you present?
No, I'm just one comment, just the extension of that question. Instead of asking the minimal energy, you ask the minimal free energy. So relative entropy to the Gibbs state. Would, in a way, be more physically more predictable.
Yeah, I have another comment. So is there a special reason why you care about the entropy of entanglement? Because the energy constraint, or the energy, like minimizing the energy is a kind of relatively, simple mathematical thing. So, and especially given that you are interested only in pure states, maybe you can consider some easier, like computationally easier measure of entanglement that gives you a satisfactory enough answer.
I think, right, you have a comment on this.
Right. Do you have any follow-up comments? Do you have any follow-up comments?
That was interesting in the pure state case. So the entropy of entanglement is kind of the standard for the case. So I mean, yeah, I guess if you use another measurement, you can solve a simpler problem. But I don't know.
Yeah, simpler questions might
Ins, yes, sure.
For example, in the.
Thanks.
Good. So any other open questions?
Thank you.
Any questions or solutions?
What if you have a solution about that? What if you go?
Maybe it's next year. Comment on why, like, so for people that have not been in the field so long, like me, aside from the reversibility thing, it's not like obviously clear why it's so important. Like what's, people keep mentioning this connection to hypothesis testing, for example. What is that connection? Maybe, I don't know, motivate. For me, it would be interesting to know why it's.
I want serious.
My brain power.
I mean, yeah, okay, but this will require preparation for the slide, which I don't have here. The point is, okay, so the environment, so my voice, I lost my voice, I don't know why, but I will do this. The point is you have a state and you want to check if it's if it's a number, or if you have a machine, yes, they prepares prepare some copies of the state, and you don't know it's entangled, then you want to essentially verify the entanglement, and how well you can do it depends on how well you can distinguish this output state from all.
It is on.
It is on. Yeah, you have to distinguish between the given state and all several states. So how well you can do it, that is exactly given by the quantum sign exponent or be. Yeah. So the point is though, the connection with reversibility I mentioned on Monday, that is the crucial kind of operational meaning. Well, in addition to the hypothesis testing, it's exactly equivalent to the question of reversibility and entanglement. So that's always like, you know, two birds with one sign. Yeah.
Thank you. All right, so any other open questions? Okay. What?
Yeah, it's also a very low effort preparation, so such is life. The problem is about understanding simple resource theories. So a couple of days ago, today we saw some things about like this. And it hasn't got exciting many copies. If there is a single measure, then theory is reversible, such and such. This question is what happens in single shot. Like if in one shot resource theory, the state convertibility is determined by a single monotone, what happens? How can such theories look like? One simple corollary is that if this is true, any two states, either rho can be transformed to sigma or the other way around, right? So that this state transformation thing, it poses a total order. The problem is to characterize all such theories. The partial result is that for qubits, for a single qubit, two-dimensional system, this is easy to do. It's basically just because majorization is a total order. So all such theories for qubits all such theories for qubits, the free state is just a ball around the maximally mixed state. And monotone is just how long is the loss factor. Okay. For higher dimensional systems, we don't know, and that's it.
Any questions?
Ask me what it's good for, because it's a clear problem.
Can you elaborate on the significance of this problem? Like, is this,
It's a cute resource theory problem, and like, if there's one place to present it, I guess it's this conference, that's it.
yeah, totally makes sense.
What do you mean by characterize all such theories?
Well, particular questions, does it exist even? Because we couldn't find out with,
So,
we can come up with one example with dimension 3, for example.
right, as soon as you get 3 dimensions, the one shot is very hard, I guess.
It's a 3x3 matrix,
Yeah,
so.
I mean, the constraints are very restrictive.
Exactly.
Those
This
stuff
is-
will no longer satisfy as soon as you put 3 dimensions.
Yeah, this is kind of our intuition, but yeah, we couldn't work it out. So,
So I guess with the 2 dimensions, the reason is because every range entity is essentially, they all maintain the same order, right? Yeah, that's pretty much where we have 2 levels, so majorization is exactly the same as
Yeah.
how far away you are from the center, so it's a single variable.
exactly.
And as soon as we go 3 dimensions, we lose that problem.
But it could be not majorization, right? In principle, disorder can be anything, as long as it's compatible with this resource theory, free operation kind of structure, it's a good resource theory.
I mean, you can of course construct hypothetical ones, like I have a state space that,
You know, I would be happy even with a hypothetical one, but even that, it's not clear how to construct it.
doing that, just geometrically, I have a hypersphere, but free operations and this stuff that gets closer to the center. And I'm allowed any rotation, and I think that works.
Well, but you have to construct, you have to be compatible with the structure of CPTP map,
Oh,
that
so
it's.
you, okay,
Yeah.
so to clarify, you want it to be compatible with the structure of C.
Exactly, it's a research theory, right?
So
And then,
already for like any set of free states, right?
uh-huh,
Any kind of distance measured to the free states that's contracted under
Yeah.
channels should be a monotone no matter what the free operations are.
yes,
So I'm guessing that requiring all of those monotones to agree on the state ordering
mhm,
should severely restrict the possibilities. Maybe it
Yes.
only ends up allowing you one free state.
yes.
So that's like Gibbs preserving or something, and then if you take that case and allow the most like generous possible
Maximal
free operations,
yes.
it seems like this isn't true already. Like this kind of simple structure.
Well, okay, so there is another possibility of such a theory where all states are free, all operations are free. Right? But yeah, I don't know. Because like we can show that in such a theory, distance to free states have to be a complete monotone. The question is like, if we just take trace distance to free states, is there gonna be a CP map that does this transformation whenever the monotone is ordered? And it seems to be not clear.
Just to confirm, you want your free operations to be CP maps, right? Like no
Okay, maybe
catalysis. or something
CPTP,
like that.
CPT.
Well, CPTP, but no catalysis or things like that.
I mean, could be an interesting question too. But yeah.
Yeah, so I just want to mention, if you allow probabilistic conversion with any probability, you can do it with a single monotone. But
Okay.
you could try to generalize that into a deterministic one, but that's the one idea I have. Yeah.
Okay, thanks. Yeah.
Questions? If not, then thank Ray again. Other open questions? Okay. Okay, let's take this final control.
Very quick, um, very quick conceptual one, but which I think is important to mention at the resource theory conference. So in classical thermodynamics, the actions that an agent is able to do is dependent on the knowledge that the agent has. So if you take Maxwell's demon or Zillardengen, whatever, and this is also related to the work the agent is able to extract and so on. So like, if I, as an agent, only coarsely understand a gas, so I only have access to pressure, volume, and temperature, and so I am only able to push a piston head, this defines the operations I'm allowed to do, and so the task I'm able to accomplish. If I'm the demon and I have knowledge of every particle, and I'm able to move every particle around, this now changes the operations I can do and also the things I can achieve. It seems to me like, in resource theories, you guys have three operations in certain contexts and so on. But how do you, or can one, have a notion of knowledge acquisition, or what observables does an agent have access to within a given task, and then start to define the operations one has access to around the knowledge that the agent has. So some example could be like, say we are talking about spins, okay? So there's like, I don't know, 100 spins in a box, and now there's some agent, and this agent is able to do Pauli measurements or something on this box of 100 qubits. The operations the agent will be able to do are going to be defined by the things that they can learn, and so the actions they can do. A different setup would be if the agent can only measure all the spins together, right? That changes the set of allowed operations. So how do you incorporate the knowledge an agent is able to acquire to the set of operations they're allowed to do? I think this is a whole in like sort of the way resource theories are framed, and it would be cool to see people working.
Right, any questions?
Are you happy if I take, the agent is correlated with the system? It's the fact that the agent knows something about it, there's just a correlation between the agent and the system. Is that a good enough answer for you?
Yes, totally. So I mean, the way I would start to try to answer this question is sort of the agent starts to do measurements or start to interact with the rest of the environment, and somehow a mutual information starts to rise, and then the agent now acquires knowledge of like the states, like sort of in a Darwinism type setup. And now because the agent has acquired knowledge of the structure of the system, to them, like they know the sort of Hilbert space factorizes in this way, and now they can touch it in this way. Then they do the operations in that way. So indeed, that's how I would start to set it up.
Thanks. I think it's a very interesting question. There's a lot of subtleties in there. In the first degree, I think some of what you're describing is like a Maxwell's demon, right? That's a demon that perceives the environment, and based on that knowledge, to the demon, the environment has more free energy than another demon that did not make the same measurement. So free energy is a concept that is very dependent on the observer's knowledge, and this is something that I think in this community, most people realize that, but outside, that's something that often people think about as more absolute, but I certainly think about it as relative quantity. But I think the other thing you touched upon, which this framework doesn't quite cover, is kind of like the coarse graining of what degrees of freedom the agent fundamentally has access to play around with. And I think partially, this is sort of like, you can think about this as the degrees of freedom the agent cannot access, as kind of like a environment. Basically, any information that's lost with those degrees of freedom is like being lost in an environment. So depending on what the agent can access, it changes their perception of what is the system they can control and what is the environment. And I imagine one can build up a framework along these lines, and there's probably related results like the Gibbs parallax and all these things where we have different colors, which tile up these things. So I think people have thought about these things from various different contexts, but it would be very nice to have some unified framework. So I think it's really interesting to think about. Thanks.
Sorry, just a small comment. One approach similar to this that I've tried in the past with Gilad is something where there's a bipartite system, A, B, and A is constrained by some resource theory. So we consider thermal operations. B is a party that has unconstrained actions, and then B can try to like do local sub-channels, like instruments, and try to assist A, and A picks like free operation. So this could be tried for other resource theories.
What is the title of the work?
Resource theory under conditioned thermal operations.
Cool. I will check it out.
And I think also like Adesso and maybe Camille Pozzecco is involved in this. They've done things like this.
I just wanted to second the call for this being teamwork. In particular, I think this is one of the ways this quantum resource theory might actually be useful to the world. In that this operationalizes or could operationalize realistic systems in a way that is largely unaddressed by the work that we've seen this week. And as someone that works with actual things, that would be really quite nice. And so thinking about how quantum states work and how we interact with them in a way that has grounding in laboratories would be lovely.
Maybe another comment. So yeah, I think in related work, so Paul Rikas, so from the quantum thermal community, worked with me like a year or so ago on looking at the relationship between the agent's memory, his belief in the state of knowledge of the world around it, versus the actual state of the knowledge around it. And whenever there's a discrepancy, there's an extra heat dissipation. So when we look at Landau's erasure and we think about it in reversible, we define a particular mechanistic method of doing that erasure process. But that mechanistic process makes an assumption about the distribution of the object that we're erasing. If that assumption is different from the actual distribution, you end up with a difference that's at least a relative entropy between the actual environment and the agent's belief state. And this actually has a lot of consequences when you want to build a modular computer, because your gates, we can't optimize them for specific input distributions because we don't know where they will be placed in the circuit. So even though theoretically you can achieve reversibility and Landau's limit, in any actual practice, when we try to build a modular architecture, just classical or quantum information processing, we end up with this extra dissipation. So there's a lot of interesting sort of things that we need to consider once we consider the limitations of what the agent can do. So I think there's a lot of interesting ideas to explore.
Okay, so there are many discussion right here. So let's keep this discussion online because of time. So let's thank Jacob Yan first. And let's thank all the speakers in this open problem sessions. Yeah. Okay, thanks very much. So there should be a walking tour today. So Graham, do you want to give a quick comment or?
Yes, so it was